Ampere's Law 3. The figure shows the cross-section of a thick current-carrying wire, and we wish to find expressions for the magnetic field when little r is less than big R and also when little r is greater than big R. Unlike an earlier scenario, however, the current density J is not uniform over the cross-section, but instead is a function of the distance r from the wire's center line, according to this equation, where beta is a positive constant. What this equation is telling us is that the current density is increasing the further out we go from the center line of the wire. We will use Ampere's law, of course, but the trick will be finding the current I that is enclosed within the various Amperian loops. Generically, current density is current per area, and therefore current is going to be current density times area. But here, since J is varying, we need to use that calculus-like form, where dA is the area of an infinitesimally thin ring, and it's equal to 2 pi r dr, which has a constant J because it's so thin. All right, let's get into this. Enough of the background. What we have here is a thick wire, and the current density is changing as we go away from the center line of the wire. What we need to do is we need to break this wire into a bunch of tiny little rings, each of thickness dr, and in the first case we're only taking little r out, not all the way to big R. And so if you look at this little ring that I've drawn in here, obviously I've drawn it much thicker than it really is, but it has thickness dr. It's a distance r, little r, from the center line of the wire. And you see I've pulled it out here kind of to the right and down. And do you see that the area of this little guy, if I pulled that thing out and I flattened it out, it would be a really thin rectangle of length 2 pi r, because that's the circumference of that thing. And then it has a little thickness dr, which means the area of that is 2 pi r times dr. Whenever we are going to use Ampere's law, we're first going to have to find the current that is enclosed, because each of these little rings has a different value of the current density. What we're going to end up doing is something like this. The current is going to be the current density multiplied by the area, and we are going to have to integrate that from little r equals 0 to little r equals little r. The equation for the current density is beta times r squared, so I've included that here near the bottom of the page. And then dA, as we showed above, is 2 pi r dr. Now, if you put all that together, you can see that there's a constant of a 2, a pi, a beta. The r squared times the r, that becomes an r cubed, and you end up really integrating r cubed dr, which gives you 1/4 r to the 4th. And then if you put those integration limits in there, there's your enclosed current when little r is less than big R. So we're going to use that in Ampere's law here in the next step. Now we have to do the same thing with the case when little r is greater than big R. The only difference is here that our integration limits, the integration limit, you see, it ends right there at big R. It doesn't go all the way out to little r. Little r goes past the actual radius of the wire. So we need to stop integrating right there when we hit the edge of the wire. Other than that, the formulation is the same here. Whenever little r is greater than big R, we're going to end up with this expression here at the bottom right. Feel free to stop the video if you want to verify this on your own, but I don't want to waste your time here by walking through every little step of that when you could stop the video and do it on your own. What we're going to do now then is we're going to use those equations for the enclosed current with Ampere's law. So let's do that. Let's do it for the case where little r is smaller than big R. Here we go. Mu naught, and then the I enclosed which we found on the previous sheet here, was 1/2 beta pi little r to the fourth. And that's going to be equal to the magnetic field strength dot producted with us going around that little loop. Well, the value of the magnetic field is going to be constant, and you end up integrating all the way around the circle. When you do that, you just get 2 pi r. Some things cancel here. We got the pi canceling. I got one of the r's canceling. We're going to put the 2 underneath. So I think what we're going to end up with here is beta is 1/4. There we go. Can we see that? Sorry, not beta. The magnetic field magnitude, 1/4 mu naught times beta times r cubed. So in terms of our graph, what that means is the magnetic field strength is increasing proportional to r cubed as we get out to that point right there. Steep curve there. The magnetic field is proportional to r cubed right there. What's going to happen as we get further away? We would expect the magnetic field to get weaker, wouldn't we? Let's see if that is in fact the case. Now we're going to take our I enclosed equation. Let me flip back here real quick. Our I enclosed equation for this case, which is right here, 1/2 beta pi big R to the fourth. So let's put that in here. 1/2 beta pi big R to the fourth. And that's going to equal the same integral. Once again, the magnetic field strength is going to be constant at each particular location of little r. So that means that we can pull that outside the integral. We're going to end up integrating all around the circle, which is 2 pi little r. And what happens here? Not as much cancels. The pi cancels. The 2 can go in the denominator there. So the magnetic field strength for this case, I believe, is going to be 1/4 mu naught beta r to the fourth, and then there's a factor of r in the denominator. I could put that 4 in the denominator next to the r, but that's good enough for now. If you want to make it look a little prettier, you can put the 4 right here next to the little r in the denominator. What does that equation tell us about the strength of the field? It says, oh, as little r keeps getting bigger, it looks like the magnetic field is dropping off, which is what we expected. Not as steeply as it had been growing, maybe kind of like that. There we go. Right here, the magnetic field is proportional to 1/r once we get outside the wire. So that's a pretty tough problem.